In 1900 Berlin, physicist Max Planck faced a troubling mystery. Classical physics couldn't explain blackbody radiation. When calculating how heated objects emit light, the equations spiraled into absurdity, predicting infinite energy at high frequencies, the so-called ultraviolet catastrophe. Planck, meticulous and reluctant to abandon classical ideas, tried something bold. What if energy wasn't continuous, but instead came in tiny, discrete packets, quanta? Introducing what became known as Planck's constant, he crafted a formula that fit experimental data perfectly. Though he considered it a mathematical trick, this idea cracked open a new understanding of nature. Einstein, a few years later, embraced Planck's quanta and applied the concept to light, explaining the photoelectric effect by proposing that light came in particles, photons. Niels Bohr then used quantum ideas to describe how electrons jump between energy levels inside atoms, shattering the classical model of the atom. By the 1920s, quantum theory had evolved dramatically. Heisenberg introduced the uncertainty principle, declaring fundamental limits to what we could know. Schrödinger developed wave equations describing particles as probability clouds. Dirac's work predicted the existence of antimatter, discovered later in reality. What began as a reluctant tweak in Planck's equations became a revolution. Quantum mechanics revealed a world built not of solid, predictable objects, but of uncertainties, dualities, and probability. The universe was no longer a machine, it was a mystery, alive with strange laws that defied intuition. Quantum mechanics wasn't just a scientific advancement. It was a transformation in how we understand reality, lighting a path into the subatomic world and changing everything from physics to technology, forever.